also know if she can borrow a chemistry book to finish her sheet, and she'll bring it back 6th period.
Sure, grab one of those. All right, VIRP charts. If you made it to equilibrium in chemistry, or you had chemistry AP, VIRP charts are kind of like ice boxes. And if you didn't have that, you probably played Sudoku. Anyone played Sudoku in here?
I'm horrible at it, but yeah.
Yeah, but you basically know the basic rules. And if there's a gap, you can figure out what the gap is. Well, that's how VIRPs work. So a VIRP chart is a handy tool that allows us to know what the potential, current, and resistances of every element, and then the power, which turns out to be very, very handy. So this is what you do. You draw V equals IR and P. So do Ohm's law, V equals IR and P, and then the elements along this side, and make a grid. Now, I'm going to use multiple colors. You don't have to use multiple colors, but I find that it tends to work pretty well if I make all the currents one color, all the voltages one color, and all the resistances one color. So after I've made my grid, I write down what I know. And what I know is the battery is 45 volts. I also know R1 is 5 ohms, and R2 is 10 ohms, because it tells me. That's all I know. And in case you're wondering, yes, this is the circuit that we evaluated yesterday. This is why I'm showing you the tool now today that we've already done it. Okay. Now in Sudoku, you can find out what's missing in any column or row or box. Same way with VIRP charts. So we know that there's something missing in this column. So anytime there's anything missing in a column or a row, then we can fill it out using Kirchhoff's laws and Ohm's rule, or Ohm's law. So what do you want to write down next? R for the first row? So the battery's resistance is the sum of 5 and 10. Remember, because the 5 and the 10 are in series? Look familiar? Okay. So battery is at 15 ohms. Mr. Byers, how did you get that? Well, the 5 ohm and the 10 ohm are in series, so we add them together. When we have resistors in series, we just add them together. So it's 15 ohms. Hey, look, a hole. Let's fill it. How do I fill that hole? Yeah, so we're going to use Ohm's law. 45 divided by 15 is normally what? 3 amps. 3.0 amps. Good. Uh-oh. What do I do now? We remember that in a series section, which all of this is a series circuit, positive, negative, currents traveling that way. In a series circuit, what's the same everywhere in the circuit? In a series circuit, what's the same? The current. Remember, if there's only one path on the freeway, we can only travel as fast as the slowest person, right? If there's only one lane, we can only go as fast as the slowest person. If there's only one path, then the current can only travel as fast as the slowest charge. So everywhere in a series circuit, we find the same current of 3.0 amperes. This is critical. This idea is very, very important. I need you to give me a thumbs up if you understand what we just did. Okay, so this is Kirchhoff's second law, where if there's 3 amps going out, there better be 3 amps everywhere in the circuit. Next, what's left? We're going to do power last. We're going to do power last. So volts. So what is the potential of R1? 15 V equals IR. So I times R, 3 times 5 is normally 15 volts. Yep. And R2? 30 volts. So 3 times 10 is ordinarily 30 volts. Great. And then we check our work twice, realizing once Kirchhoff's second law, or is it first law? Kirchhoff's first law tells us that the voltage in R1 and R2 must equal the voltage coming out of the battery. Does 15 plus 30 equal 45? Yeah. Last thing. Solve for the power. Now, I don't call it VIRPiv, but we can call it VIRPiv if you want. Power is IV. So solve for the power in each element. Yes, yeah, absolutely. Yeah, you can also use I squared R if you want. And I use power as a check, but if you have power and you're missing one of these, you can use I squared R and IV to solve for any of these two. It's a very beautiful chart. Okay, so what's the power of the battery? 135? And the unit is how, what? Watts, okay. And R1's power? 45 watts, 3 times it. And R2's? 90 watts. So does the power coming of the battery equal the power that's dissipated in each of the elements? And it's better. No matter what kind of circuit we're dealing with, how big or complex it is, the power in each element should equal the power at the battery. Okay? Give me a thumbs up if you understand what we just did.
Yes.
Excellent. Okay. Then I have a question for you. Don't blurt it out. I want you to talk about it. We'll take a vote. Of R1 and R2, if rather than just plain old resistors, if R1 and R2 were light bulbs, which would be brightest? Take 30 seconds, chat with your neighbor, then we'll take a vote. And the same is not an option. So it's either R1 or R2. That's the thing. 5 seconds. Okay, if your neighbor thinks R1 is the brightest, raise your hand. 1, 2. Okay. If your neighbor thinks R2 is the brightest, raise your hand. Everyone else. Way to go, everybody else. Okay, so how do I know that R2 is the brightest? Who can tell me why I know R2 is the brightest?
Well,
Sure.
I wasn't really sure exactly though, but all the numbers were higher, so I just assumed that it would be the brightest.
Okay, but there's one number in specifically that's important. Griggs? The power. What is power? Power is energy over time. In other words, a watt is a joule per second. So every second, R2 is pumping out 90 joules of heat and light. Every second, R1 is pumping out 45 joules of heat and light. Does that idea make sense? So if someone wants to know what is the brightest, what they're really asking you is, every second, which device is pumping out the most joules? So power in watts is how many joules you pump out every second. Does that idea make sense? Okay, give me a thumbs up if you're ready to move on. Okay, so we talked about series circuits. Now we're going to talk about parallel circuits. We briefly mentioned parallel circuits last time. And in parallel circuits, when we add paths, the overall resistance does what? It decreases. Like you're cruising along on the freeway, and you get past the railroad casino, and then you get to the wagon wheel, and now all of a sudden you have 3 lanes. What happens to your traffic? It speeds up. So that's how current works too. Even though you're adding a resistor, if anytime you add a path, you reduce the overall resistance. And we use the reciprocals. Okay, look familiar? Okay, I mentioned this last time. I'm going to mention it again. If you had trouble with the reciprocals with optics, then be very, very careful because we have reciprocals again. Okay, so in a parallel circuit, here's a simple one we're going to evaluate in a second. In a parallel circuit, the current in each individual path has to sum up to be the current that provided those paths. In other words, if you have a road cruising along and that road breaks into 2 paths, if there's 20 cars here and 20 cars here every second, how many cars were here? 40. Okay. So if you had 20 amps in that branch and 20 amps in that branch, you better have had 40 amps in that branch. Okay. And if they come back together, how many amps are here? 40 amps. Excellent. Okay. And the great thing about a parallel circuit is each branch has the same access to the battery. Let me show you what I mean. Here's our parallel circuit. Each branch has the same access to the battery. This branch sees 90 volts. This branch sees 90 volts. This branch sees 90 volts. R1 doesn't even realize R2 and R3 are there. Okay. Parallel circuit. Let's VIRP it. Make your VIRP. Make your VIRP. VIRP, VIRP, VIRP. By the way, this is an old style. This is an old style notation for a battery. I mean, for a generator. I'm just going to go ahead and make it a battery, just because it's easier that way. That's technically a term for a generator. So battery R1, R2, R3, and that's it. And buyers need new black pens. Buyers black pens have issues. Next, write down what you have. Write down what you know. What's one of the things we know? Battery's 90 volts. Excellent. What else? R1 is 60 ohms. R2? 30 ohms. And R3? 20 ohms. Okay. That's everything we have. You're done scribbling your chart together. Okay, so where do I start? The battery's resistance. I have a hole up here, so let's solve it. I have a 60, a 30, and a 10 in parallel. So to solve that, I'm going to use my reciprocals. I'm going to go 1 over 60 plus 1 over 30 plus 1 over 20, and then that's going to be 1 over RP. So 1 over 60 plus 1 over 20 plus 1 over 30, enter reciprocal, or enter x over 1, or enter x to the negative 1 power, whatever your calculator happens to have. 10? Do we agree it's 10 ohms? How can that be? The smallest resistor is 20 ohms. How can the equivalent be 10 ohms? Math. Yeah, exactly, math. That's just the reciprocals. So when you have parallel sections, you need to have your equivalent resistance. Please make sure that is lower than all the pieces, because that's reciprocals. Okay? What's next? Current at the battery. Can you find the current at the battery? Am I going too fast? A little fast. Okay. So how do I get 10? I took 1 over 60 plus 1 over 30 plus 1 over 20 because these are in parallel, and then I hit enter, reciprocal, and that gave me 10 ohms. So in other words, these 3 resistors together are equivalent to 10 ohms. As far as the battery is concerned, it's seeing a 10 ohm resistor. It doesn't know that it's seeing a 60, a 20, and a 30. Now we have a gap in the middle, so we can solve for current. Anyone solve for current? 9 amps. 9.0 amperes. Uh-oh, there's a big block. We have to use what we know about circuits to fill something in.
9.0.
What about it?
All of them?
No, because this is 3 separate paths. If this was series, then we'd say 9 amps all the way down.
90 volts. Voltage
90 volts. Exactly. In a parallel section, each parallel section, each branch sees 90 volts. This branch sees 90, this branch sees 90, this branch sees 90. So we can just take the 90 volts and copy the 90 volts down to each branch. And now we can finish it up with current. So I will let you do that. Finish my table up by finding the current at each individual item. making some of you have filled out your chart. Sure.
Can we just go back to the slide where it's a series so I can just see the difference between the thing,
This one?
okay, yeah. No.
Okay. So what is the current through R1? 1.5 amps. And the current through R2? 3.0 amps. And the current through R3? 4.5 amps. So is all the traffic through R1, R2, and R3, is that equal to the sum of the traffic through the battery? So in our road split into 3 pieces. So 1.5 plus 3 plus 4.5, does that equal 9?
Yes.
Good news. Okay. So again, all the current that traveled through the battery or out of the battery traveled through the paths and then came back together, go through the battery. Hooray, Kirchhoff's rules. Next, power. Find power. Sean, you got the power?
Yes.
What's the power of the battery?
810 watts.
810 watts. And anyone have the power at R1? Sure. 135 watts. And R2? 270. And R3? 405. Does 405 plus 270 plus 135 plus 810, or sorry, plus 1, do these equal 810? Great. Now last time, you told me that R2 was brightest and R2 had the highest resistance. There's going to be a challenge slide later on that's going to tap into this. Which of those is the brightest? It's not a trick. R3, yeah. Every second, R3 pumps out 405 joules of energy. And R3 is actually the lowest resistance. In the previous series circuit, it was the element that had the highest resistance that was the brightest. Here is the element that has the lowest resistance that's the brightest. How weird. Why? Math. Exactly, math. Okay? Does this idea make sense? Okay, that's a parallel circuit. Any questions about parallel circuits before we move on to something a little more complex? Not by much. Okay. Combination circuits. Combination circuits are called combination circuits because they're a combination of circuits. So if you have a combination of circuits, you call your combination circuit a combination circuit.
That's not a combination.
So the simplest combination circuit I can come up with is a combination of series and parallel sections. One series section, one parallel section. And when you get a combination circuit, it's going to look like that. Then what you do is you break the parallel, or you compress the parallel sections into virtual resistors. Ooh. You can probably skip part 2 if you want to. But I'm going to show you how to do it in a second. If you want to write down the rules, be quick about it, because I want to get to the VIRP chart. If you just want to get to the VIRP chart like me, then you can just make it V equals I, R, and P. There's going to be a battery. There's going to be an R1. There's going to be an R2. There's going to be an R3. I think that's it. 1, 2, and 3. Yep. Still copying the rules? Again, if you use the VIRP chart, the rules, you don't even need them. They're just, yeah, you do it automatically. Okay, moving on. Okay, here's our combination circuit. Our combination circuit has a parallel section and a series section. There's a series section, an 8 ohm resistor in series with the battery, and there's a parallel section. why it's called a combination circuit. Let's write down what we have. We have 60 volts in the battery. R1 is 8 ohms. R2 is 30 ohms. And R3 is 20 ohms. And I believe that's all the information that we have. So what do we do? Here's the thing. We can't add up the resistors because this isn't just a series circuit. And we can't use reciprocals because this isn't just a parallel circuit. It's a combination circuit. So what we do is we compress R2 and R3 into a virtual resistor that doesn't really exist but allows us to do the math. So I'm going to make a little box between R2 and R3, and it's going to represent the virtual resistor R23. This is going to be R23. And we're going to find it just like we find any other parallel branch. Doesn't touch. So what is the equivalent resistance of R23? Maybe tap on your calculator. Ask Siri. Siri, what is the equivalent resistance of R23? 12 ohms? That's what the back of the room got. What's the front of the room? 12 ohms? Okay. So what we're basically saying is we can compress R2 and R3 into a virtual resistor, R23, that is equivalent to 12 ohms. Does it exist? No, it's a virtual resistor. But it does allow us to do math and make the math a lot easier. So R2 and R3 get compressed into R23. And I like to make little boxes on the lines when I use virtual resistors. I find it just makes things easier. So I'm going to put a little voltage box and a little current box. Okay, what's next? Exactly. Now we have a situation where R23 is in series with R1. So we can add R23 to R1's resistance just as though they're in a series circuit because they are. So what is 8 plus 12? Yeah, 8 plus 12 is usually 20. So the battery sees 20 ohms. And we're off and running. I like to. You don't have to, but I would strongly recommend it. If you have a virtual resistor, I find it's easier to be consistent, but you don't necessarily have to. Okay, so what's the current at the battery? 3 amps? So 3 amps. Okay, great. What's next? Good question. Would R1 be 3 amps? Yes, it would. R1 is in series with the battery, so R1 is also 3 amps. You know what else is 3 amps? R23. Because R23 is in series with R1. Cool. What do you want to do next? Voltage of which? R1. Can you find the voltage there? What do I do? How do I find that? 3 times 8 is 24 volts. Now what? 36 volts. And does 36 plus 24 equal 60? Yay! We're almost done. Almost done with the combination circuit. Okay. Now we're stuck here. Yeah, question. Nope. Because they're in parallel. In parallel, each branch shares the same voltage. In parallel, each branch shares the same voltage. So if the equivalent resistance is 30, or equivalent potential is 36, that way because R23 represents a parallel section. So since it represents a parallel section, and each branch in a parallel section gets the same voltage, then R2 and R3 both get 36 volts.
In parallel, all branches share some voltage.
Yep. What's the same in parallel is voltage. What's the same in series is current. Okay. Can you finish this?
Yeah.
Yep. And those two amperages should sum up to 3. So in other words, since R2 and R3 is 3 amps in the virtual resistor, it has to go somewhere. So 1.2 amps in R2, 1.3 or 1.8 amps in R3. That would be power.
You have power for
No, excellent question. There is no power in a virtual resistor because it doesn't really exist. It's not something that can dissipate energy. The virtual resistor doesn't really exist. You can solve for it and you will get the power that will be useful, but it may actually just be confusing. What I recommend doing as a check, if you're using power as a check, then just do the power of each actual element. Yeah?
Is this just a good way to solve it, or is this the format where you solve problem concepts?
Both. You can solve it different ways. I've seen what used to be done before we started using VIRP charts is people would just start scribbling numbers all over each element, and it became exceptionally difficult for teachers to grade. So we found VIRP charts work really well because I can look at your work and know exactly where you went right or wrong. So yeah, you'll encounter, when you go to college, you'll encounter teachers, or you'll encounter students who weren't taught this way, and they're just going to throw numbers, they're going to puke numbers all over the diagram. And you're going to see ohms and voltages and current all over the place, and then you're going to have this, and you can be like, this is how you do it. And they'll be like, that's so wonderful, and you can teach them how to do it. I know, because I taught a couple of physics teachers how to do this. Yeah.
My mom taught me basic numbers.
The puke numbers, yeah.
That's she showed me
It
how to
makes
do it.
grading really hard on your professors and your teachers. This makes it really easy, and it's actually easier to keep your information, organized. Okay, so what power did you get for the battery? 180 watts. And at R1? 72 watts. And R3? Or sorry, R2? 43 watts. And R3? 65? 65 watts? Okay, cool. Now, rounding is going to be an issue. Later on, when you actually have real resistors you're working on, rounding will be an issue. When you round the proper number of sig figs, you'll get numbers that are approximately this. They'll approximately add up. It's going to be good enough. Okay, cool. Which one's brightest? R1. And then? R3. And then? R2. Just looking at that resistor or looking at that circuit, I wouldn't know which one's brightest and by how much. This information tells me this. Okay, questions? All right, it's the piece de la resistance. Boom. We have 11 minutes. Let's work this guy out. Frequently, the battery will be given to you, but not always. Here, the battery's potential is not given to you, but the current at R4 is given to you. I missed. Everything is given to us. This is 5.25 milliamps. Some of you have had some issues with metrics. Please be careful. Milli is 10 to the negative 3. This is 0.00525 amperes. Oh, and yeah, we have 3 sig figs. So we're probably going to run into a rounding issue. That's okay. Okay. So how should I begin this? Find the volts in R4? That's a great idea. Now, did you do it yet? So let's use Ohm's law and find out how many volts are going through R4. $3.5? 3.54? Okay. So we got 3.54 volts in R4. Excellent. Now, I will tell you right now that there is no one right way to solve this circuit. You can solve it backwards, forwards, and sideways. As long as you're completing the table, you can actually do it in a different order than I do it and still get the exact same answers. Question or answer?
Question.
Okay.
Since R2 and R3 and R4 are all parallel, would that mean they're the same volts?
That's exactly what it means. Everybody hear that? He asked, since R2, 3, and 4 are parallel, does that mean they have the same volts? And yes, it exactly means that. So since we found that R4 has 3.54 volts, that means R2 and R3 have the same thing because they are branches of a parallel section. See, the crazy thing is we're actually solving it in the exact opposite way period 4 solved it, which is cool. I wish I recorded period 4 because I could show you both ways. They went to the battery first and then came back. You guys are going eventually to the battery. Okay, so now that you have the voltages at R2, 3, and 4, can you give me the currents at R2 and R3?
R2 is 0, or 0.014. R3 is
0.011?
Yeah, well, I rounded up.
Okay, sounds good. 2 sig figs is just fine. All right. We'll pause here and let everybody catch up. Okay. What's next? You want to find the resistance of the battery? Great idea. How would we find the resistance at the battery? Exactly. Let's compress our 2, 3, 4 into one big virtual resistor. So we're going to compress this into a virtual resistor that looks like this, and it's going to be R2, 3, 4. By the way, that wasn't the only thing to do. You could have gone a different direction. You could have realized that something equals something. You could have realized that R2, R3, and R4, all the current through R2, R3, and R4 had to first go through what? It had to go through R1. So solve it however you want to solve it. Yeah. If you add up R2, R3, and R4, you will get the current of R1 and the battery. Because R2, 3, 4 follow R1, whatever current traveled through R2, 3, 4 had to first travel through R1 and had to come from the battery. Does anybody have the equivalent resistance of our virtual resistor yet? 117.9? Kind of round up to 118? 118 ohms. The resistance?
Yeah, of that virtual.
255 and 325 and 675 with their reciprocals. So 1 over 255 plus.
Same formula you did to find the battery, but it's like a virtual one.
Yep.
Or the virtual
Yeah. So let's one over 675, and then enter reciprocal.
Okay, so you use the same formula on
Yep. So our virtual resistor has a value of 118 volts, or 118 ohms. Did anybody total up the currents yet? How much? Oh, I'm sorry, the currents. Did anybody sum up the currents? 0.035? 0.03. 30? Like that? And the total resistance of the battery is how much? 263? Okay. 263 ohms. Hey, we're in the final stretch. Jared.
Okay, so I just wanted to, because I thought you said if we added up R2, R3, and R4, you know, that the red box, I thought you said that that also equaled R1's amp.
Current. So the virtual resistor, if you wanted to add a virtual resistor, that current would equal this current. Because whatever current left R1 got split into R2, R3, and R4. So if I wanted to do a virtual box here and a virtual box here, then the current would be the sum of these. I didn't because I didn't need to, but you can totally do that.
How'd you get
That was all.
Taylor added that to that to that.
Okay.
He did, like,
Because whatever current was in R2, R3, and R4 had to come from R1. It's like the road split into 3 pieces, then came back together. All the traffic on the road split into 3 paths, and then came back together again. R1's potential? 4.35? 4.35 volts. And what's left? Battery voltage and current. Okay, so 2 ways to go about this now. We have 3 minutes left. We can add R1 to R2, 3, 4's voltage, and that's going to be the voltage at the battery using Kirchhoff's first rule. Or we can realize that all the current that traveled through R1 came from the battery using Kirchhoff's second rule. So let's just do both. So the battery should get 0.030 amperes because whatever current traveled through R1, which is in series with the battery, had to come from the battery. Or we can realize that the voltage drop at R1 and 2, 3, 4 had to sum up to be at the battery. That looks like about 7.9? 7.8 something? 7.89? Okay, 7.89 volts. Okay. So let's do power and see how we did. Hammer out the power and we'll see which one is best, which one is brightest, and who wins. Who wins the bright contest? So Sean, you're going to go home and teach your parents how to do VIRP charts?
my mom.
Teach your mom how to do a VIRP chart?
Sure, why not?
It's like, Mom, you got to stop puking numbers all over the diagram. Got to learn how to be organized. Okay, which one was brightest? R1 was brightest? What did it get?
13.05.
13.05? Okay, cool.